Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. We saw in this playlist that if you have global solutions to a Diophantine equation, that gives you local solutions, whereby local solutions I mean solutions in the p-adics. And one of the reasons why it's good to look for these local solutions is the fact that the existence of these solutions is very easy to determine. And the reason for that is because of Hensel's lemma. And this lemma is a very general form of the implicit function theorem that I mentioned in a previous video. Okay, so to talk about this, just as in the implicit function theorem, you need to talk about derivatives. So we need to talk about derivatives in a fairly general setting. So let me show you how that works. We're going to start with the commutative ring R. And if you think about how Newton and Leibniz introduced calculus, they added an infinitesimal, I'll call it epsilon, and the key point in all the calculations is that when you squared epsilon, you got 0. Well, in algebra, we can make actual sense of this by introducing the following ring, R epsilon. So what is that? It's just a quotient of the polynomial ring with coefficients in R, Rz, modulo z squared. And so we can let epsilon be the coset containing z. And the key point here is that if you square this element, of course, you get the coset containing z squared, which is 0. So that's how you can adjoin an element epsilon, which is itself not 0, but its square will be 0. So if you want to think a little bit about what this looks like, you can think about it as a module over R, in which case you can write it as just R direct sum R times epsilon. In other words, every element in this quotient ring you can write as an element of R plus R times epsilon. And that expression is unique. Okay, so let's see how we can look at derivatives. And unfortunately, this only works for polynomials. So we fix a polynomial f of x, say the sum of fi x to the I, with coefficients inside our ring R. And what do we normally do when we define the derivative? Okay, so what we can do is we copy the usual definition. We use the difference quotient. So what we can do now is we can look inside the ring Rx and also adjoin this epsilon, where epsilon squared is 0. And once you do that, what you can do is you can substitute inside this ring x plus epsilon into this polynomial. So that gives you f of x plus epsilon. And you can also substitute in x, which is also inside here, and take the difference. And normally when you divide by epsilon, that gives you the derivative, f prime of x. Of course, you can't divide by epsilon inside here because epsilon squared is equal to 0. But what is true is that if you multiply both sides of the usual definition for the derivative by epsilon, you get a true equation. So in other words, if you look at the difference of these two, you get f prime of x times epsilon. So this is something that holds inside this ring here. And this derivative here, this you can use as the definition for the derivative of f, is given by the usual formula. Okay, it's just the sum of I times fi x to the I minus 1. And the version that we'll use of this is the following. It's more adapted to what we want to do. So we're going to pick two elements, R0 and R1, inside our ring. And let's suppose that R1 satisfies the same property as epsilon. Its square is 0 inside this ring. Then we can also substitute R0 plus R1 into this polynomial and subtract f of R0 from that. And the usual formula now holds. This is equal to the derivative of f. You have this polynomial, you substitute in R0, and you multiply this by R1. Okay, so let's just briefly think about why this is true. So the proof of part 1 actually follows by the usual calculus proof. This is something that's completely algebraic and mechanical. And what facts do you use when you do this? Okay, when you compute this formula here using the usual calculus proof, the main thing you use is just the fact that when you see this epsilon squared, you make it 0. And the point is here, you can do that because by definition, epsilon squared is actually equal to 0. So that calculation, which requires normally delicate limit proof now just holds on the nose. So that's rather interesting, and it allows you to give a sensible definition for derivatives of polynomials, and it's just what you expect it to be, and it does what you expect it. So what about the second part here? How do we prove this equation here? Well, all we have to do is the following. So it's essentially very similar to what you see over here. We've just specialized x to r0 and epsilon to r1. And why can we do that? Well, the key point is that if we look at this ring here, r adjoint x and epsilon, where epsilon squared is 0, we have a ring homomorphism from here to here, where we just send x to the r0 and epsilon to r1. And it is a ring homomorphism because r1 squared is equal to 0. So that's the only thing really you need to check that that's a ring homomorphism. So if you use that ring homomorphism and you apply it to this equation here, the left-hand side just maps to the left-hand side here, and the right-hand side just maps to the right-hand side here. And that's why this equation follows from this one here. So that's rather nice, and this is something that we'll be using to establish Hensel's lemma. Okay, so to be able to present Hensel's lemma, I need to say some basic facts about the completion. So remember, to get a completion, what do? We pick an ideal, and in this case we'll look at a maximal ideal, this Gothic M. And this completion of R with respect to M was given as some subring of an infinite direct product of quotient rings. So it was a subring of R mod M cross R mod M squared cross R mod M cubed, and so forth. So sometimes I'll abbreviate that with R hat. And since there's a subring of this infinite direct product, you can map this ring to each of these quotients, since the direct product also maps to each of those quotients. So for example, I can map R hat onto R mod M just by projecting onto that first factor. And it's quite easy to see that, of course, this is a ring homomorphism, and in fact, it's even surjective. So using the first isomorphism theorem, you can get certain results about the kernel M hat. What can you say about the kernel M hat? R hat mod M hat is isomorphic to the image here, which is R mod M. And this will be a very important ring for us. Since M is a maximal ideal, this will be a field, and it's called the residue field here. Okay, I want to present some nice facts about this completion. So the first one is the following. Okay, if you have an element A inside this R hat, or also there's a parallel statement for R mod M to the I, can we easily check that it's invertible? And the answer is yes. So when is it invertible? Well, all you have to do is to look, well, in this case, modulo this M hat, or in this case, modulo its maximal ideal M mod M to the I, and check to see whether it's non-zero there. Okay, so this is a condition for invertibility, which is quite easy to check. And the reason for this is quite easy to see. So the basic idea is as follows. You can think of this element A as some sort of a power series. So that's roughly the type of objects that you find inside this completion. So you can think of it as a power series. So what does this condition here kind of correspond to? Well, it corresponds to the fact that the constant term is not zero. And when you have the constant term not zero, it's easy to invert such a power series. So that's roughly the reason why it's true, and you can turn that actually into a proper proof. So that's the case for the power series, and actually the same sort of idea proves it in this case here, where you have R mod M to the I. The other thing that's rather interesting is that, well, you've projected this R hat onto R mod M, the first factor. I guess you can project onto any factor that you like. So you can try to project R hat onto R mod M to the I. And of course, that's something that's interesting to do. But actually, it's something that can be described using the data we have already, so we don't use new notation for it. okay, if you look at this ideal here and you raise this to the power of I, then you will find that it is equal to the kernel of this map here. So you also get the fact that R hat mod the ith power of this M hat is also isomorphic to R mod M to the I. To state Hensel's lemma, we need to introduce a little bit more notation. So I'll use the bar notation to denote the residue class modulo the maximal ideal. So in other words, if R is an element of the completion R hat, or of a ring R mod M to the I, then R bar is the residue class modulo M hat in the case of the completion, or M mod M to the I in the case of R mod M to the I here. We'll use similar notation also for polynomials. So if you have polynomials with coefficients in R hat, or in this ring here, when we reduce modulo M those coefficients, we'll use the bar notation. And I'll give a little example of that to make that absolutely clear. Okay, so let's have a little look at an example. Suppose we consider the polynomial f of x equals x squared minus 7. Remember, the integers sit inside all the rings of p-adic integers, so you can think of this also as an element of z hat p. And so this is a polynomial with coefficients in z hat p as well. Some of the things that we've looked at, we can look modulo the maximal ideal p, and then take the derivative. So here will be just 2x. And we can also substitute numbers in there. So I could substitute, for example, 1 in there. So this gives me 2. And what's interesting with derivatives in this case is that, well, if you're going modulo p equals 2, so modulo 2 is equal to 0. So that's a 0 here. Whilst for p equals 3, you get, well, just the usual 2 times 1. So that's 2. So this is some interesting phenomena that occurs when you work in positive characteristic. When you take derivatives, you can suddenly look at a polynomial like this, and when you differentiate it, well, actually, if you go modulo 2, then this becomes the 0 polynomial. Okay, now we're ready to state Hensel's lemma. So Hensel's lemma is about solving equations, polynomial equations. So suppose we have n polynomials with coefficients inside R hat, and they're in n variables. Okay, so the number of variables equals the number of polynomials here. So what we'll do is we're going to suppose we have some n tuple of elements in the residue field, so that's A bar, and basically this is going to be a solution modulo the maximal ideal. Okay, so that's what we're going to assume. So that's what we have here. What does it mean to be a solution modulo maximal ideal, or rather 0 modulo the maximal ideal? That means that when you look at each of these polynomials and you reduce all the coefficients modulo the maximal ideal to get fi bar, and you substitute a bar into that, you get 0. And that should hold for every I, so for these n polynomials here. So basically you have a solution modulo the maximal ideal, which in the case where this is the ring of p-adic integers, is just a solution modulo p. Okay, so as in the implicit function theorem, the derivative has to come in as well. And what we see here is now we look at the partial derivatives of fi bar with respect to xj. So since the number of polynomials is n is the same as the number of variables, this is going to be a square matrix. And you can ask that the determinant not be 0. Okay, so that's a non-degeneracy condition. And if you pick polynomials at random, I guess you'd expect it more likely that this would occur than not. Okay, so under these conditions, what does Hensel's lemma tell us? So this is the wonderful theorem that Hensel proved. It says that in this case, you can find an n tuple of elements inside the completion, which both lifts this solution modulo the maximal ideal and gives you a solution, or rather a 0, to all these equations. So in other words, if you substitute this a into the original polynomials, which have coefficients in R hat, you'll get 0, so you get a solution over R hat. And furthermore, if you look at all the coordinates of this A, so like the ith coordinate of this A, that's some element inside the completion of R. and you look at that modulo m hat, so that's an element of r bar. That's the original ai bar, the ith coordinate of the solution that you put here. Okay, so basically it's saying that this solution that you had, modulo the maximal ideal, lifts to a solution inside the completion of R. And so the importance of this is that, well, it produces for you solutions over R hat. So existence of solutions over R hat is given by, well, you have to satisfy the hypotheses. Well, essentially, the main thing is this one here, which is existence of solutions over R bar. So often, using Hensel's lemma, you can reduce finding out whether there exist solutions over R hat to the question of whether there exist solutions over R bar. Of course, there's an extra condition to check, so that comes into play as well, but more often than not, this will hold. So the proof for this is actually quite nice, and the key case actually is when n equals 1. And the way you do it is you actually construct the solution A. So the other thing good about this method is that it's constructive. It's not just existential, you can actually construct it. And it's constructing by defining A modulo powers of this m hat for larger and larger powers of this maximal ideal. And you do it by induction on this value of j. So remember, in the special case, in particular, this works when r equals the integers and you take the completion with respect to some prime ideal. So in that case here, finding solutions over R bar means finding solutions mod P. And that's a finite problem because there are a finite number of elements in Z mod P. So that's fairly easy. So the hard thing is to find solutions modulo all powers of the prime, because that's infinite. But what this is basically saying is that actually you can work out how to solve that infinite process, and the key thing is the base case here. To prove Hensel's lemma, we need to see how the algorithm works, and the easiest way to look at the algorithm is to look at a simple example. So I'll give you a sample algorithm right here. So the polynomial that I want to have a look at is the following quadratic polynomial we looked at before, f of x equals x squared minus 7. And we'll think of this as a polynomial with coefficients inside the 3-adic integers, z hat 3. And so remember, one of the things that we saw, of course, the derivative of this f prime of x is 2x. So we'll need that to invoke Hensel's lemma. And to use Hensel's lemma, we need to have a solution modulo the maximal ideal, which means a solution modulo 3. So in this case, let's have a look at this polynomial modulo 3. What is it? Well, 7 is congruent to 1 modulo 3. So basically, you're looking at the zeros of x squared minus 1. And of course, the easy way to pick a solution is to just let x equal the residue class of 1. So f bar of 1 bar is equal to 0. So we know this is a solution modulo 3. And to get a 3-adic solution, we'll work bit by bit. What we'll do first is we'll lift this solution modulo 3 to a solution modulo 3 squared. So how do we do that? Well, basically, it's got to be a lift, so it has to be 1 plus some multiple of 3. This makes sure that if you reduce this modulo 3, you get back this solution here. Okay, so we're going to pick A1, that's some number which is either 0, 1, or 2. And we want to pick it so that it gives you a 0 to this polynomial, modulo 3 squared. So f of 1 plus A1, 3 is congruent to 0, modulo 3 squared. So how do we do that? Well, I guess if you don't know anything about this, you can just try firstly the case where A1 equals 0 and look at f of 1 and see how close do you get to 0 modulo 3 squared. Let's just see what happens. You substitute 1 into here, you get 1 squared, and then you subtract 7. So this is equal to minus 6. and that's modulo 3 squared, so it's actually not 0. So we don't get a solution if we put a1 equal to 0. So I guess the question is, well, if we put a1 equal 1 or 2, can we make this 0 mod 3 squared? So the best way to solve for this a1 and show that you can do that is to look at the difference of these two congruence equations. So let me show you why that's the case. If you look at the difference of these two, you get f of 1 plus a1 3 minus f of 1. If you look at the difference of the right-hand side, you get 0 minus negative 6 is just 6. And the key point is that this here is the numerator of the difference quotient. And furthermore, when you square this term here, a1 3, when you square it, you get 0 modulo 3 squared. So that means that you can use those facts I told you about derivatives to rewrite this in the following way. It's the derivative of 1, and you're actually allowed to take this modulo, the maximal ideal, times this a1 3. So now we have an equation involving this a1, and we just ask, can we solve this new congruence equation here? Okay, so let me just show you why we can indeed do that. We'll note firstly that 3 divides both this term, and the modulus. So we can divide 3 from all those 3 quantities, okay? So we divide 3 from here, we get the derivative at 1 times a1, divide this 6 by 3 to get 2, and divide the modulus 3 squared by 3 to get modulo 3. And now we have, miraculously, an equation which is actually inside Z mod 3. It's equation modulo 3. And we need to solve it. Okay, so we'll need to know the derivative of this f bar at 1 for that. So the derivative of f, of course, is 2x, and we're substituting in x equals 1, so that's 2. But the most important thing is that for Hensel's lemma to work, we need this derivative to be a unit. So this is a unit in Z mod 3. So of course, since it's a unit in Z mod 3, we can divide by it to solve for a1 in this congruence equation. Now, of course, in this particular case here, it's pretty easy to see what the solution is. But in general, that's the reason why you need this derivative to be a unit. This is the thing which allows you to solve this part of the equation. Okay, once you've used this formula involving the derivative and the difference quotient, you can solve the resulting equation because this is a unit. And in this case here, of course, a1 just equals 1. So we do have a solution, modulo 3 squared. So what is it? It's 1 plus a1 3, where a1 equals 1. So that means it's just 1 plus 3, or 4. So 1 plus 3 is our solution, modulo 3 squared. And so, of course, you can ask, can you get some solution modulo 3 cubed? And I'll just go through the first couple of steps in this. So I guess you want to lift the solution you have here. So the way you'll do that is you'll have to add some multiple of 3 squared. So you add a2 times 3 squared, and a2 will be one of the numbers 0, 1, or 2. And you look at the solution when a2 equals 0 and see how far off you get. So here this is 4. So when you plug that into the original equation, you'll get 4 squared. And you subtract 7. So there'll be 16 minus 7 is 9. Of course, you had a solution modulo 3 squared. So this is 3 squared. But modulo 3 cubed, it's no longer a solution. So you have to solve for this a2. And I hope you can see what happens in this step is just like what happened before, actually. Okay, so firstly, this term here, when you square it, it is 0 modulo 3 cubed, because it's got a 3 squared term here. In fact, when you square it, it's a 0 modulo 3 to the 4th. But we won't use that fact. So you can look at this term here, and again, you can look at the difference of these two terms and rewrite that out using the derivative of f. And that'll be some simple formula that involves this a2, and using the fact that this derivative is a unit, you can solve uniquely for this a2. And repeating this procedure allows you to find a 3-adic solution to this polynomial equation x squared minus 7 equals 0. Or in other words, a square root of 7 inside the 3-adic integers. So this proof is both nice because it tells you it's quite easy to find solutions to polynomial equations in the p-adic integers. You just need to find solutions modulo p and then hope that you have the correct derivative condition holding. The other thing is that it's an algorithm, so you can actually say something about what that solution is. So that gives you a lot of information about solutions to polynomial equations in p-adic integers. I hope you enjoyed this adventure in pure mathematics.